Welcome back to the second part of chapter 1, HSC board physics. Moment of inertia as analogous quantity for mass. You must have studied in class 11th what is mass and its role, kind of inertia in translational motion. So in translational motion, mass plays a role. So if you want to move any body, the or if you move any body with velocity v, it got some inertia, which is mass into velocity. So similarly, in rotational motion, distribution of mass along rotational axis plays similar role, which is defined as inertia. Now, for example, here is a rigid body which is rotating around an axis with angular velocity omega. Now, body is made of small particles which we can consider as a n number of particles of having mass m1, m2 up to mn. From a distance r1, r2 up to rn from the axis of rotation. Then all the particles, they perform uniform circular motion along the axis with the same angular velocity, which is omega. But if you look at their linear velocity, it is different. As we said in the part 1, if you want to calculate the linear velocity, then you can define linear velocity of each particle as product of the distance from the rotation axis and angular velocity. So we can say V1 is equal to R1 omega, V2 is equal to R2 omega, like that, Vn is equal to Rn omega. So translational kinetic energy of first particle we can write as half m1 v1 square, and if we substitute v1 square, v1 is equal to r1 omega, then you can rewrite that translational kinetic energy of each particle as half a1 r1 square omega square. And the rotational kinetic energy is a sum of individual kinetic energy. So you can sum it half m1 r1 square omega square plus half m2 r2 square omega square, like that. So you get a rotational energy, kinetic energy of the entire body. So we can rewrite the equation as half in bracket m1 r1 square plus m2 r2 square up to mn r square, and omega is same for each particle. So we can rewrite that equation the way it is written, which is equal to half I omega square. So in rotational momentum or in rotational motion, you can rewrite this rotational kinetic energy the I factor, which is we replaced by m1 r1 square plus m2 r2 square plus mn r square, in the form of summation from I to n particles m1 r1 mi ri square. So this I mi summation of from I is equal to 1 to n mi ri square replaces mass, and omega replaces v in rotation motion. Therefore, rotational kinetic energy is equal to half m I omega square. So that I is a moment of inertia. So moment of inertia, using the same concept, you can calculate moment of inertia of any object. Let's take as an example of how to calculate moment of inertia of a uniform ring having radius r. So we can similarly we can divide the ring in a small masses dm, okay, which is so all the dm masses are located at the distance r from the axis, which is the radius of the ring. So we can rewrite, as we see in the last page, all these masses are at rx distance from the axis. So we can define moment of inertia of one particular small mass, which is dm, as inertia of that small particle dm, idm, is equal to dm. So its mass, okay, the small particle mass dm into r square. And to calculate inertia of a ring, we need to sum up all dm's inertia, which we can write I is equal to integration from 0 to m dm r square. So dm varies from 0 to m, which is like a entire mass of the ring. Therefore, we get I is equal to m r square, because integration of dm from 0 to m is equal to m, which is the mass of that ring. So you can say moment of inertia of a uniform ring I is equal to m r square. Similarly, in the second example, we can calculate moment of inertia of uniform disk. So here is a disk, uniform disk of mass m. When we say uniform, that means it's equal distribution of mass. So with the concept of uniformity, we can divide that disk into small particle of equal masses, small mass dm. Okay, so that's why we always say uniform disk. If it is not uniform, then you cannot calculate as per this formula. Then you have to apply some other methodology. Then that problem becomes complex. For simplicity, we always say that uniform ring, uniform disk. So above is a uniform disk of mass m and radius r, rotating about its own axis. Same concept, we can consider that it is made up from number of concentric rings. So instead of masses, we can say the disk is made from outer peripheral to the center of small such rings. So the small such concentric rings, putting all together, can become a disk. So with that kind of assumption, we can take one such ring of width dr at radius r. So this particular ring is having width dr and radius is r. So the inertia of this ring, that small ring IR, is equal to mass of that ring mdr into r square. Now if you want to calculate the mass of that ring mdr, which is equal to area of that ring into the density, and area of that ring is equal to 2 pi r into dr. So dr is the width, which gives inertia is equal to 2 pi r dr rho, that will be the mass mdr, into r square. So you get inertia of that particular ring. As you calculate the moment of inertia of a uniform ring with same formula, you get IR is equal to 2 pi rho r cube dr. Now if you want to calculate the total inertia of that disk, you just have to sum up. To get the inertia of this, we need to sum up inertia of all such concentric rings. So you can easily write I is equal to 2 pi rho, which is a constant, and radius varies from axis 0 to the outer peripheral, which is r cube dr. This gives 2 pi rho r to the power 4 by 4. So substituting rho is equal to, if you substitute, if you want to calculate what is the density of the disk, then it is a mass divided by the area, and area is pi r square, which is a area of a circle. So if you substitute rho is equal to m divided by pi r square, we get I is equal to half mr square. So if you look at the inertia of, if you compare the inertia of uniform ring and the inertia of a uniform disk, the m is same, r square is same, but in case of uniform ring, most of the mass is at the distance r. So inertia is also located around that r, but in case of uniform disk, it shifts a little bit inward. So that is a kind of a difference you have. Let's understand what is the radius of gyration. Consider any object. We can define moment of inertia as so again take an example of such an object, any random object. It need not be circular or any special shape. So you can define the moment of inertia of that particular object is I is equal to mk square. If you consider mass m effectively at a distance k from the given axis of rotation, that means the mass of entire object is supposed to be uh, is concentrated at some distance, okay, which is k from the axis. Then k is called radius of gyration. So effective mass is at that distance. So k becomes radius of gyration. Now, if you want to calculate the inertia of ring, let's say along the diameter, then the distribution of mass is a little different. Or consider the case where you want to calculate the inertia of a ring or a disc along the axis which is tangent to that particular ring or disc. It becomes complicated because then the distribution of object, the r, it becomes a complex function. It's not a simple. It is not just r square. So that's why the theorem of parallel axis and perpendicular axis came into picture. So let's see what is the theorem of parallel axis. Consider object rotating about an axis which is not passing through the center of mass. Here one axis is passing through C, which is center of mass, and other through O, around which the particular object is revolving. And these two axes are parallel to each other and are separated by distance h. So similarly, same concept, consider a mass dm which is located at d. Then the moment of inertia of that small mass dm around the axis of rotation which is at O, we can write is IO is equal to the distance of that object dm from the axis which is OD. So we can write IO is equal to integration of OD square dm. So now if you look at OD, so what is the OD essentially? OD is the square of OD square is it's a right angle triangle. You can very well say OD square is equal to ON square plus ND square. Now ON is nothing but OC plus CN. So this gives A plus B square, A plus B whole square is equal to A square plus B square plus twice AB. You get OD square is equal to OC square plus CN square plus 2OC into CN plus ND square. You can rewrite that because OC is nothing but H. So you get OD square is equal to H square plus CD square plus 2HCN. So you can effectively rewrite IO is equal to integration of H square dm plus CD square dm plus 2HCN dm. Now CN dm, so CN is basically the location of mass around the axis C which is passing through the center of mass. So by the theorem, because it's passing through center of mass, the same is located, so the is sum around that axis will be 0. So that is why integration of C and dm will be 0, because on one side it is plus and exactly same mass will be located on other side of the axis, which is minus. So plus minus becomes 0. And CD square dm is nothing but the integration of CD square dm is nothing but the inertia of the object around the axis which is passing through center of mass. We treat that as IC, which means inertia, okay, of the entire object around that. So we can rewrite IO, mass of inertia of that particular object around the axis O, IO is equal to IC plus mh square. So this is a parallel axis theorem. So if you know the moment of inertia of any object around the center of mass, then you can calculate the center of mass of that particular object around any other axis which is parallel to the axis passing through the center of mass. Then you just have to do what you have to do. You have to just multiply its mass into the distance between two axes, which is h, and you just have to add that into the moment of inertia. Then you get the moment of inertia of the object around any other axis which is parallel to the axis which passed from the center of mass. So IO is equal to IC plus mh square. So this theorem is very helpful in calculating mass. I give an example that if you know the moment of inertia which is passing through the center, then you can calculate the moment of inertia which is located on the edge of the ring and perpendicular to the plane of the ring. Then you can easily calculate that. You just, what you have to do, you know the moment of inertia of a ring is mr square. Then you just have to add m, again one more mr square. So mr square will become 2mr square. So that's how this theorem is very helpful in calculating the moment of inertia in any other axis. Similarly, look at the theorem of perpendicular axis. Consider rigid laminar object able to rotate about 3 mutually perpendicular axes, x, y, z, the way it is shown. Again, same concept, consider a point mass dm located at point P such that x square plus y square is equal to z square. So if Ix, Iy and Iz are moment of inertia around the axis x, y, z, then we can write Ix, which is moment of inertia around the x-axis, is equal to y square dm, because that object is at a distance y from the x-axis. So Ix is equal to y square dm, Iy is equal to x square dm, and Iz is equal to z square dm. Substituting x square plus y square is equal to z square, we get Iz is equal to y square dm plus x square dm, which essentially the moment of inertia of that object is sum of the moment of inertia along other two axes which are perpendicular. So that's the theorem of perpendicular axis. Now look at the application of how we can apply that theorem, parallel and perpendicular axis theorem, in doing some calculation. So consider the case, calculate moment of inertia of a disk rotating along tangential axis. So here is a disk of radius r and mass m and rotating along the axis which is tangential to the disk. And we already know the disk inertia along the axis passing through the center is half mr square. So which is like perpendicular to the disk, axis passing through the plane of perpendicular to the plane of the disk at the center. The moment of inertia is half mr square. which we can say it is Iz, because xy will be in the plane of the ring, disk, and I will be the perpendicular. So as per Perdue theorem, Iz is equal to Ix plus Iy. And in this example, it's a disk with a radius r. So Ix and Iy both will be same, because if you calculate Ix, you also calculate Iy has to be same. Means Ix is equal to Iz by 2 if you sum up. So this gives Ix is equal to mr square by 4, because Iz is equal to half mr square, again divided by 2, mr square by 4. Now x axis and axis of rotation is parallel by distance r. So by parallel theorem we get the moment of inertia which we want to calculate is equal to Ix plus mr square. If you put the value of Ix, which is mr square by 4 plus mr square, you get I is equal to 5 by 4 mr square. So that's how you apply the parallel and perpendicular axis theorem to calculate the moment of inertia around any axis. Now let's look at what is angular momentum, and it is how it is analogous to the linear momentum. So angular momentum or moment of linear momentum. So once you have linear momentum, then its moment also, because that also we can treat as angular momentum. So again, consider mass or a body rigid object rotating along axis, any axis which is constant, rotating with a constant angular velocity omega. Similarly, consider a small masses at a distance r1, r2, etc. and it is rotating in uniform circular motion. So we can say that each small particles having a linear speed v1 is equal to r1 into omega, r2 into omega, etc. So linear momentum you can define for each particle is equal to p1 is equal to mass into velocity, linear velocity. So p1 is equal to m1 v1, and since v1 is equal to r1 omega, you can say p1 is equal to m1 r1 omega, p2 is equal to m2 r2 omega. Similarly, pn is equal to mn rn omega. And angular moment of each particle is nothing but the linear momentum into the distance from the axis. So you can write angular momentum of each particle L1 is equal to P1 R1, which is in turn becomes M1 R1 square omega. L2 is equal to M2 R2 square omega. Ln is equal to Mn Rn square omega. And the direction of angular momentum can be obtained using the right hand thumb rule, similar to the way you calculate the direction of angular velocity. And as they are in the same direction, all those angular momentum, you can add it algebraically, like L, which is the angular momentum of that object around that axis. L is equal to m1 r1 square omega plus m2 r2 square omega up to mn rn square omega. So you get m1 r1 square, m2 r2 square plus mn rn square omega. But m1 r1 square plus m2 r2 square plus mn rn square is nothing but the moment of inertia of that object around the axis around which it is revolving. So you can replace that by I. You get the expression for angular momentum L is equal to moment of inertia into angular velocity. So that's how the moment of inertia plays a role of kind of a mass in case of translation phenomena. So the way in translation you can define the momentum is equal to mass into velocity. Similarly, the angular momentum is mass of inertia into angular velocity. So which is analogous to P is equal to mv. So we look at the expression of torque in terms of moment of inertia. Again, we consider same kind of a example, having the object rotating around and having masses m1, m2 at distance r1, r2, and each is having now in this case it is revolving around that axis with an angular acceleration alpha. So linear acceleration of each particles we can rewrite as r1 into alpha linear acceleration of second mass a2 is equal to r2 alpha, like that. And force experienced by each particle, so force is angular mass into acceleration. So for the force which is realized by the particle m1 will be f1 is equal to m1 a1, and if you replace the value of a1 you get m1 r1 alpha. Similarly, f2 is equal to m2 r2 alpha, like that. And torque is nothing but the product of force into the distance. So torque expressed by each particle will be like force into distance. So in that case, particle 1 will experience a torque tau 1 is equal to f1 r1, which is equal to m1 r1 square alpha. Tau 2 will be f2 r2, which is equal to m2 r2 square alpha, like that. And as direction of each torque is along the axis of rotation, we can sum up algebraically, and we get tau, which is the torque in terms of moment of inertia, tau of that entire object, which is revolving around the axis with angular acceleration alpha. We can sum it up as a t1, tau 1, tau 2 up tau n, and we get tau is equal to m1 r1 square plus m2 r2 square plus up to mn rn square into alpha, which is essentially moment of inertia into alpha. So which is analogous to the translation motion phenomena of force is equal to mass into acceleration. Let's look at the conservation of angular momentum, the way there is a conservation of linear momentum. Again, same example. Everyone is going under the translation momentum p1, p2, pn, etc. So angular momentum is equal to the linear momentum multiplied by the distance from the axis of rotation. So to calculate the rate of change of angular momentum, we differentiate the above L is equal to R into P. So if you do differentiate, dL by dt is equal to R into dP by dt plus dR by dt into P, which is how you differentiate the product of A into B. So now dR by dt is equal to velocity, which is the rate of change of which is the linear velocity of each object, and dP by dt, which is a force, so because change in momentum. So rate of change of momentum, that's a force, and P is equal to mass into velocity. Therefore, you get dL by dt is equal to R into F plus m v into v. Now, v into v is the cross product of itself, which is 0. Therefore, you get dL by dt, which is the rate of change of angular momentum, is equal to R into F. But R into F is the moment of is the momentum of a force or torque. Okay. So if tau is equal to 0, then we can say dL by dt is equal to 0. Therefore, we can say L is constant because the derivative of any constant is equal to 0. So essentially, that proves that conservation of angular momentum. Next topic, rolling motion. Now here consider a tire of radius r pushed on the road, it will move forward. So once you push it, it will have translation velocity v and also angular velocity omega. Let's say this mass has m and k is the radius of gyration. So here is an example. The tire we pushed and it has a translation velocity and angular velocity as well. So total kinetic energy of rolling object, the tire, is equal to translation kinetic energy plus rotational kinetic energy. So you can write the total kinetic energy E is equal to half mv square, which is the translation kinetic energy, and rotation is equal to half I omega square. I is moment of inertia. And if k is the radius of gyration, we can rewrite I is equal to mk square and omega is equal to v by r. Okay, so we can rewrite E equal to half mv square plus half mk square into v by r whole square. If you rearrange, you get the kinetic energy of a rolling body is equal to half mv square into 1 plus k square by r square. So in case of radius of gyration is 0, then it becomes total kinetic energy becomes half mv square. So that example was on the plane's horizontal plane. Now consider the linear acceleration and speed while pure rolling down an inclined plane. So the mass m is at height h at rest and having potential energy mgh, because any object which is above the ground at distance or height h will have potential energy mgh having mass m. And when it comes down, this potential energy translates into kinetic energy, which is a kind of a translation plus rotational. Look at this animation. So this is how it will roll. So you can write E, which is the energy of that object in discussion, is equal to mgh, and when it converts into kinetic energy, we can rewrite half mv square plus 1 plus k square by r square, as we did right previously. So this gives v is equal to square root of 2gh divided by 1 plus k square by r square. So linear distance traveled, so if it travel, the inclined distance is s, we can write in terms of height h is equal to s is equal to h by sine theta. As you can see, you can derive from the trigonometry of that figure here. And you know that the formula of translation formula 2as is equal to v square minus u square. So if you use that, you can put s is equal to h by sine theta. So we get 2a h by sine theta is equal to, which is v square is v is the final velocity. So we can write, substitute v is equal to 2gh divided by 1 plus k square by r square minus final velocity, initial velocity will be 0. So you essentially get acceleration is equal to g sine theta divided by 1 plus k square by r square. So that's how the linear acceleration and the speed of the object while pure rolling down an inclined plane. So that essentially is the end of chapter 1. Thanks for watching, and in near future I will explain you how to use all those concepts of rotation dynamics in solving the problem. So keep watching the videos, follow my videos, subscribe. Once you subscribe, the moment I put a new video, you will get a notification and you can immediately refer to the new videos to understand the concept of rotation dynamics and also other concept of physics or maths which I will put in near future. Thanks again for watching.